So, good afternoon, everybody. Welcome to our seminar, weekly seminar on quantum information and quantum chaos. We are going to start soon. I'm very pleased to welcome all colleagues and collaborators, local from Krakow, from our department, from the neighboring department, from math department, and also people from outside Krakow. I'm pleased to welcome guests from Warsaw, Marek, hello Markus from Gdańsk, hello Vinayak, now from South Africa. Fereszte is now in Krakow. So I'm very, very pleased to introduce to you our new collaborator. Simon is originally from Australia. Then he had a postdoc in UK, in London, and now he arrived during COVID to Krakow. And I'm very, very pleased to announce his talk. And he promised us to tell us something about category theory applications to quantum information in a relatively easy way. So, Simon, the screen is yours. Please continue with your talk.
I think you are muted, Simon. Yes.
Simon, yes. Simon, we cannot hear you so far.
Okay, it's fine.
Okay, so thanks for inviting me to talk about this. I think that every year or every 2 years, for the last few years, I've given the same or a very similar talk trying to understand quantum codes using category theory. And every time it really, I feel like it's not so successful. But then some time goes by and I forget that this happens, and I discover some new things and get excited again and want to tell people again about what I've discovered. So here I am again, excited to talk about this. And I'd really, if people want to make comments or questions, I'd really like that as well. So yeah, please interrupt with comments and questions. I thought I'd start with some kind of motivation, and this is not necessarily the only motivation, but these are some things I've been thinking about. And just in the context of quantum physics, the Schrödinger picture is, I guess it's about states, quantum states. And then the Heisenberg picture is more about the linear maps or the unitary maps between state spaces. And right, so I would say that when we're talking about quantum codes, maybe the first thing that you try to do to write down a state in a quantum code, if you try to understand quantum codes this way, it gets very painful very quickly. So it was Gottesman and some others that came up with this idea of defining a quantum code by the operators that stabilize the code space. And I would say that this is an example of Heisenberg picture thinking. We're not dealing with individual states, we're dealing with entire spaces of states, vector spaces. But there's higher pictures here, and I guess the idea is that we're talking more about operations, and each higher picture is about the operations on the lower picture. So some things that live down here are topological quantum field theories, which I know a bit about. conformal field theories, which I know much less about. String theory, I don't really want to know about. But also things like high energy physics, which is dealing with representation theory of Lie groups. And I would say that the direct ket is also here. I'm going to explain what I mean by this in a moment, because it's a simple example of what I'm talking about. But these higher pictures keep going, and I don't really know much about what is down here. We need to wait for the mathematicians to come and explain this stuff to us. We might be waiting a long time. And I guess in this talk, I'm not really actually going to explain what a category is. I'm going to just give examples. And I think this is my favorite way of learning things, is to see a lot of examples. And then I get the picture, I get the idea of after that. So that's what how this talk is going to be structured. And we're going to be talking about a little part of what's down here. So I guess it's one step more operational than the Gottesman picture. A basic example of a category is the category of sets. And just to introduce you to the jargon of category theory, we have objects, and these are sets. The objects of this category are the sets. And I'm going to use letters like this to denote objects. Maps between objects are functions. So this notation, this hom notation, is supposed to be the set of maps from A to B. And I just wrote it over here like that. And that's another notation. F is a function from A to B in this category. And I'm going to put the category over on the left here so we know where we are.
Sorry, just to...
Carol.
Yes. You showed the notation HOM. It stands for some homo something?
Thanks for that question. Yeah, so HOM stands for homomorphism.
Yes. Okay.
I forgot that. I just say HOM whenever I see that. Yeah. So I'm going to, people don't usually call this tensor product of sets, but just because I want to give a uniform treatment of how tensor product works, if we were going to find a tensor product in this category, it would be this thing, that where we take the pairs. A tensor product of two sets is just the set of pairs from the two sets. So please stop me if this doesn't make sense. And there's a unit for the tensor product. It's just a set with one element. And then there are these maps that just, so the tensor product of I with any set, it's just going to put a star next to all the elements of A on the left or the right. And so the unital maps just forget about the star. And there's also a swap map, which just reverses the order of each of the elements of the tensor product. I guess people usually call this the Cartesian product of sets, but I'm calling it the tensor product. And now this is a bit more tricky. It's saying that functions from the Cartesian product, the tensor product of A and B to C, is the same as functions from A to functions from B to C. And this is what computer scientists call currying. So what it is a function that takes two inputs is the same as a function that takes one input and gives you a function that takes the other input. So now I'm switching to another category. The objects here are finite-dimensional vector spaces over a field. And in quantum physics, we're used to using complex numbers. I'm not really going to talk about complex numbers today or adjoint or complex conjugation. So I'm just going to talk about vector spaces over a field. And the maps between these objects, these are linear maps. And I hope we're all reasonably familiar with this category. This is really where the tensor product lives. And I'm using this ket notation now. And so this notation is supposed to mean the vector space with basis A, B, and C, ket, tensor with the vector space with basis D, E, F. It looks like this. And the unit for this tensor product is just the underlying field. And we could also think of it as a one-dimensional vector space over this single ket. And then there are these unitor maps that work very. The reason why I'm writing all this is it's supposed to remind you of what we just did in the previous category, the category of sets. But now there are these scalars. It's like every element in our set has a scalar weight associated. And this is what I was talking about with the ket operation. This is like the foundational axiom for quantum physics, that the ket takes a classical label, a set of classical labels to a vector space. And it's just the vector space with that basis. And this notation is supposed to make you think of that. That's really how the ket is working. So the ket is a map between categories. They call these functors. And the same currying isomorphism exists in this category.
So it is the map between index, set of indices, and vectors.
Yeah, something like that. It's easiest for me to understand this when I write everything with a basis.
Okay.
Yeah, it really does carry over from the category of sets. And I guess the other thing to notice about this, I didn't really write this down, but this is really important, that the home in this category is a vector space. So we can talk about mapping from a vector space A to this home vector space. But there's something in this category that's new. We can take dual objects. This is the dual vector space. It's this space, the vector space of linear maps to the tensor unit. That's the underlying field. And we get this magic formula, which is the foundation for things like the Choi-Jagiellonian isomorphism. Set doesn't have duals. If you try mapping from a set into the unit object, there's only one map in here. So you just get back I. So none of this stuff works in this category of sets. The category theory jargon for what's going on here is that this category is compact closed. So every object has a dual, and there are these unit maps and co-unit maps, and they satisfy a bunch of equations. I didn't write down what this unit map is, but it's essentially the identity map, and the co-unit map is the natural pairing of a vector and a covector. And there's all this notation, string diagram notation, which people might have seen for expressing the equations that all of these maps satisfy. And this string diagram notation, this is supposed to be a picture of quantum teleportation, which I'm not really going to explain today, but oops, there are all these great references that I just want to mention. that talk about how to use string diagrams to do these kinds of calculations in this category. This is like going from less complicated to more, or it's going from more concrete to more abstract here.
Simon, just a short
Yep.
question concerning the references. They seem to be very new, and this idea to use category theory to quantum information was initiated somehow like 10 years ago or 15, or they are not the first references in this field, or they are the first? Well, could you hear me?
I'm very sorry. I think I didn't catch your question, but
No, the question was simple: whether there exist earlier references concerning those issues.
Absolutely. So I feel this really goes all the way back to Einstein notation, where indices that are duplicated are supposed to be summed over. But it wasn't really until Roger Penrose came along that he was the one that started expressing these tensor equations using these kinds of string diagrams. And that was in the 60s, I think. So yeah, there is a long history of this stuff.
Thank you, thank you. Fine.
But particularly for quantum information theory, these notes by Biamonte are really great. And also these other references are good as well. And I also have to say that I was very skeptical about this string diagram notation until it came time to do my homework for one of my graduate courses. And I found until I started using it, I was very skeptical. And for me, it actually really helps to keep track of the subsystems that you're composing with and multiplying and other tensor products. And conversely, if you want to make your paper look really complicated, stay away from string diagrams, because the equation that this string diagram corresponds to, it's a big mess. So that always makes papers look much more impressive. Okay, so now I'm going to try to use our what I've been explaining. Someone's not muted. So now I'm going to try to take what we've been doing in these two categories, the category of sets and the category of vector spaces. I'm going to move into another category and try to do some of the same things. Now the objects are what's called, these are graded vector spaces. What does this mean? What we have is a sequence of vector spaces, and each vector space is indexed with an integer. I guess I'm going to call this the grade. So vectors now are going to live in one of these grades. Some people try to take a direct sum of all these AI things, but I prefer to just keep it as a sequence. Maps between graded vector spaces are, this is a bit complicated. So how am I going to say this? I guess
what are those vector spaces? Are they, like, I don't know, contained in each other or something?
No, it's just a sequence of vector spaces.
Okay.
Yeah. Arbitrary, infinite sequence of vector spaces. Let me try to explain what's going on here. What we want is that the home between two graded vector spaces is also graded. So there's going to be an index here, I. So the index I is going to be this sum of vector space Homs. And you can see that it's bumping up the grade here. So let me show you a picture. I'm going to choose a Hom, a particular map here. And now the grade is going to have, this is going to be a sequence of, how do I explain this? There's going to be a grade 0 here, and it looks like this. So F0 is going to be a bunch of arrows like this that map the grade, the corresponding grade for A over to B. F1 here is going to bump up the grade. F2 is going to be like this, F-1, F-2. And I guess the idea is that this Hom AB is a graded vector space, and it's built from the underlying Homs of the vector spaces. So let's talk about the tensor product of two graded vector spaces. This is also going to be graded. So at grade I, it's this thing. This is like a convolution product. And there's a picture. So I'm doing A tensor B here. So I've got the grades of A over on the left, the grades of B down the bottom, and I'm only just showing 3 grades so far. And yeah, so we're taking the direct sum over where the sum of the grades of the, oh wait, there's a typo here, that should be B, should be BK there. So the direct sum is along these green lines here. So grade 0 is this middle one here. You can see that the grades -1 + 1 adds up to 0, 0 + 0 adds up to 0. And then this one, I guess, is grade 1. And then the next one is, that's grade 2. That's, yeah, so, yeah.
What do these grades correspond like physically? I mean, because they are just indices,
Right.
as I understand them. But
Right, right. This is a good question. I guess abstractly, they don't correspond to anything. And I guess you're asking why are we learning about this? And
there's a good example in the chat by Marcus Grassel as for the multivariate polynomials, homogeneous polynomials of fixed degree. I can see it in the chat. That's a good example of a graded space, vector space.
Yep.
Okay, thanks, Marcus, for this example. Yes, thank you, Mark.
There's another good example, which is these are super vector spaces. And instead of grading over integer grades, you just grade over odd and even. So that's kind of string theory stuff, I guess. Okay, there's also a unit for this tensor product. And if I just reuse the diagram that I just showed you, the unit is just, in grade 0, we have a copy of the field, and then there's zeros everywhere else. And it satisfies this equation. And you can see what happens here, that these are the only non-zero vector spaces. All the other ones get killed. So we just end up with the A's again showing up in all the grades. So that's how this equation works. Duals, right? So graded vector spaces, we do the same. This is the same equation that we were using for vector spaces. So how does this work on graded vector spaces? Well, we do the same thing. We map A into the unit for the tensor product. And so this is grade 0 is just the usual A star. So grade 0 of the dual is the dual of the 0 grade of A. grade 1 is now, it's the dual of the negative grade of A. So this grading, so once we take the dual of these graded vector spaces, we reverse the grading and we get the dual of the underlying grades. So that's, in general, is what it's going to look like. The dual of a graded vector space flips the grading and then takes the duals. So, okay, if that, I know I said at the beginning that I like learning things by example, and these are supposed to be examples of categories, but actually I'm kind of violating my rule, which is examples of these. Yeah, so we really want to see examples of these, of the examples. But I'm already showing you another category now, which is the category of chain complexes. And objects here are still the same graded vector spaces, but now we have these differential operators. And they're purely concentrated in grade -1, and they square to 0. And if you haven't seen this before, this is horribly abstract, so I'm not sure what to do about that, but I will just get to an example very soon, I promise. And with the maps between chain complexes, these are really going to be the same as previously, but explaining how these things become chain complexes is kind of complicated. I'm actually going to skip that, but it does work. Right. So this is a picture of the D map that's of grade -1. So it's mapping down by 1 grade, and people just tend to write it like this, just mash them all together. And people also tend to put indices underneath the D, but I'm not sure what notation to use there. I'll just stick, yeah. There's a conflict with notation, putting an index underneath the D, because this is really all D -1. Okay, so this is a ridiculously simple example. And what it is the graded vector space is 0 everywhere except A0 and A -1. And A0 is 4-dimensional, A -1 is 3-dimensional, and this is the D map here. I wrote it out in matrix form, and the dots are 0 entries. And this D squared equals 0 is easy, because if you follow any of these 2 arrows, you're going to get 0, because this is the only non-zero map. So this is a 0 map here. These are all zeros. So this is a ridiculously complicated definition of a binary linear code as a length 1 chain complex over Z mod 2. I kind of didn't mention that we switched to just integers modulo 2. The code space is the kernel of D. In this case, it's just the all ones vector. That's the only thing that gets through this matrix, gets mapped to 0.
Mm-hmm.
Yeah.
Simon, and
yeah.
Could I have a simple request? Do you plan to remind us what such a linear code is in not such a complicated setup, but in a more simple words?
Yeah.
So we could somehow appreciate.
Yeah, I like to think of this. Yeah. So I guess, yeah, the idea here is that we're sending 1 bit of information, and we're going to send it in 4 bits. So this is classical information. And the idea is that instead of just sending 1 bit, we duplicate it, we copy it onto 4 bits, and then we use this D matrix to check if any of our bits got corrupted. And so if any one of these ones got flipped to 0, the D matrix is going to detect that. We're not going to get the 0 vector out.
And is it like standard repetition code?
This is a repetition code. Exactly right. Exactly right.
Okay.
Another way I like to think of this is as a simple icing model. Now there are 4 classical bits, and then I guess the Hamiltonian has these 3 check operators that check that the adjacent bits agree with each other. Right, so this D is called the parity check matrix because it's checking to see if any of these bits got messed around. Right, so within this framework of chain complexes, the classical codes just live here. You just have these checks. But you could imagine that there are some redundant checks that if you could measure your checks perfectly, you don't need them. But if there was some noise in your check measurement, then you could use these meta checks to check the checks. And that can keep on going. And this kind of stuff does show up in quantum codes. And so this is what I'm going to get to next is what are these co-checks? And once again, this is a crazy complicated definition of what a quantum code is. So now we have 3 non-zero grades. This correspond to grade 1 here, grade 0, and grade -1. And there are 2 differentials here. And if you already know about quantum codes, I've put these Z letters here to remind you that these are the Z checks of the stabilizer code, and these are the X checks of the stabilizer code. And then the D squared equals 0 is just saying that the Z and the X checks commute. So this is a translation of the Gottesman theory of stabilizer codes over into this world of chain complexes over Z mod 2. So the co-checks are this guy, and the checks are this guy. And I guess I don't have any examples to show you, but yeah, in the literature, there really are codes showing up with meta checks and so on, and meta co-checks. So this really is a kind of more general picture of codes. Okay, so now I want to think about the tensor product of...
Simon, sorry, one remark or question. That's really only applying to CSS type codes.
Exactly, yep.
Not to general ones.
Yes.
Am I right?
That's right, yeah. Yeah, I made sure to stick that in there, yeah.
Sorry, so please remind the audience the meaning of CSS. It stands for...
I guess it's that there's no operator that has mixed X and Z type terms.
And those
So it's Kellner-Bank-Shor-Steen codes, and for those you are separating the stabilizers into some that check the X errors and some that check the Z errors.
Okay.
Yes.
Independently of each other.
So,
So it's a restricted class of codes.
Felderbank, Steen, and who is the third?
Kellner-Bank-Shor and Steen.
Ah, okay. So good. Thank you.
Yeah, thanks. Okay, I hope I'm getting closer to the punchline here. We're going to start talking about tensor product in this category. And I'm going to start off with the simplest possible example that we've been looking at, this repetition code. and I'm going to try and take the dual tensor A. And this is reusing the previous picture that I was showing you. So this is, I guess this is grade 0 in the middle, grade -1 down here, grade 1 up here. And there's this funny stuff with the duals. And I haven't told you how to turn this into a chain complex. I'm really only looking at the graded vector spaces here. It's not too hard to see that we could take this D and tensor with the identity matrix, and we could construct some arrows down here. But I'm not showing that today. I'm just focusing on the graded vector space structure. And I talked about this previously, that the dual, when you take the dual of a graded vector space, you flip the
I don't know if Simon has some problems with the connection, or it's just me.
I think Simon has some problems with the connection. Yes.
Okay. Well, there's nothing but further to do but wait, I guess.
Yes?
Oh, okay, he's back.
Yes.
Yes, you need to unmute Simon. And you're almost silent. I don't know why.
Can you hear me?
Yes, say it again.
Hello?
It's somehow not so clear as before.
Yes, you're almost silent. That's strange.
And what has changed, Konrad?
I don't know. Nothing. I mean, he just had some problems with connection. And
is that better?
yes.
No, much better, much better. Please continue.
Okay. Yeah, I apologize for my bad internet connection. I don't know how much of that you caught, but this is the key here, that this tensor product of a classical code with its dual gives you a quantum code. And those are the three grades. The three grades. So the Z type checks live here, and the X type checks live down here. Here's another picture. This time I really did try to make it look like an icing model. So this check, the three checks here correspond to the three vertices on this little picture. And and then the four edges here correspond to the input of the check matrix. That's the F4 here. And the dual flips the role of the edge and the vertices, the edges and the vertices in this picture. And now we can take the tensor product of these little diagrams, and you can see that this vertex times an edge gives you an edge. And I haven't drawn it here, but the edge times an edge gives you a face. And there's this thing is the surface code. And when you stick in other classical codes for A, you get all kinds of other interesting codes. And originally this was called the hypergraph product. I think around 2011, this was discovered. And right, these are some of the best quantum codes that we know of. Google, right, keeps talking about how they're going to build a big surface code in the next 10 years. And the theory of these hypergraph product codes, I guess that maybe it's not state of the art anymore, but for a long time, these were the best quantum codes around.
By the way, the best in which sense? How do you quantify quality of a code?
Yeah, so that's always a tricky question. I guess that you want, I guess you want a family of codes, and this family includes arbitrary large codes that get the distance of the code is increasing, and you'd also like the rate of the code to increase as well. So for the surface code, there's only ever one quantum bit stored, no matter how big it is. But in general, these hypergraph product codes, they will store more and more qubits the bigger they get. Right, so this is the punchline, and this is why I got, this is kind of the excitement that made me want to talk about this today, that we were talking about this before in the category of vector spaces, that you can construct these homes using the tensor product and the dual. And this still works in this category of chain complexes. So that means that we can use string diagrams to talk about tensor product, quantum codes and tensor product and maps of codes. Maybe I can try to say a little bit about what's going on here. So if this string was just a classical code, then the time goes upwards in these pictures. So this is the classical code, and then at this time here, this is like a 3-dimensional surface code, and then we go back to the classical code over here. So this is supposed to be some kind of logical operator in the surface code, and then this is I think this is like a measurement of a logical operator, or anyway, I guess I'm going to finish around about here. So yeah, I think that's enough.
So I'm not so sure. Have you already reached the conclusion?
Yeah.
Well, fine. So then let me thank you for the talk.
Thanks.
Yes. So let us start the discussion. We have now a lot of time for questions and comments. Who would like to be the first to make a comment or ask a question?
So this grading in graded vector spaces corresponds to an errors. When you go to the a previous index, perhaps you have lost a bit or something.
Yeah, right. So I guess I'm always putting the code space in grade 0, and then the errors always occur in grade 0, and then you have the checks that I guess in grade -1 are the syndromes, the result of the check operators.
So, okay, so what grade 1 corresponds to? If, I mean, the -1 is the results of an error.
I know, it's kind of weird. This is really a superposition of the co-checks. So it's like one of these spin liquids. It's like some kind of spin liquid of superposition of co-checks going on here. I mean, maybe you really do need to think of the dual of this quantum code as well as, so you really need to think of A star as well as A, because these co-checks also, these are check operators as well. So yeah, but here they're transposed.
Yeah, this is strange. I don't think I understand it all.
Let me try something else. So topologically, the grade 1, the dimension is off by, the dimension is missing, is missing by 1. So grade 1 corresponds to the faces of this. Grade 0 corresponds to the edges on here, and grade -1 is the vertices. That's the topological picture. That's why they call these topological quantum codes, because they're constructed from this manifold that you kind of put this cell complex on the manifold, and then on the vertices of the cell complex, you associate X checks. On the faces, you associate the Z checks, and on the edges are the quantum bits. So there's a quantum bit on every edge. Okay. If you haven't seen this stuff before, it's really difficult to.
Yeah, it is.
Sure, it's This is why I say that every time I give this talk, it's kind of a disaster, because it's really like you should take several days to go over this stuff. But I guess the thing that got me excited was this string diagram stuff. Hey, these string diagrams are used to talk about teleportation in quantum information theory, but the same string diagram applies to these tensor product constructions. So what does that say? And I don't know the answer to that.
Yeah. So thank you again. And now I see in chat there is a nice statement by Philip. Philip, would you like to read your message again?
Yeah, of course. I mean, it was related to the question about these checks and co-checks, is that whenever you put the co-prefix in front of something, it turns things that you don't understand completely into things you completely don't understand.
Yeah.
So nice. This is the case with many things in category theory.
Yes. So I see now the co word. Yes. Very nice. Very nice.
I also have a question.
Yes.
Do you have an example for some? So how do these meta checks and meta co-checks look like?
Yeah,
they have sort of higher order. Not. Is it just this manifold more complicated?
That's right. So if you go to the 3-dimensional toric code, you get these meta checks because your checks. How does this work? Your checks correspond to faces of a 3-dimensional complex, and they should all add up to a closed volume. So the meta check is like a volume. It's saying that all the check operators that indicate an error should be closed.
And in the case of low density parity check codes, you probably don't want very high meta checks, right? Because the more and more.
Well, right. So if you start with a generic LDPC code and you take a tensor product and you do it again, if you take a triple tensor product, you do get these meta checks for any input. Yeah.
I meant considering like low density parity check codes where you don't want to have syndrome measurements of high weight, this sort of line with checks and meta checks, there will be very few, or there will be sort of a strict cutoff, no, at some point, I can imagine. So there won't be, say, any meta checks. Is that? Okay, it's very loose. It's very hand waving everything. But,
yeah. Fine.
Yeah, you might be right. Yeah, you might be right.
Any other remarks or questions?
So I may ask a question if no one else has any ideas.
Yes.
At the first half of the presentation, you mentioned that we may think about cats like about some functors from set category to category of vector spaces.
Right.
And in this case, the example was kind of trivial because we may physically interpret it as moving through from classical mechanics to quantum mechanics or something like that. And my question is whether we've got a good example or some intuition for some functors from category of vector spaces to category that you discussed.
I guess a lot of these examples do look very simple and straightforward. Yeah, there's some kind of free construction. So I think there is one that goes from the category of vector spaces to the category of graded vector spaces. And all you do is just include your vector space in at grade 0. I think that works. That's now like the free graded vector space on a vector space. But yeah, that's a good question. This is the kind of thing that keeps category theorists up at night, thinking about all these different functors and how they relate. Yeah.
And Simon, one more simple question. You use the name of toric codes. Could you possibly explain us where you see a torus? What is here has a topology of a torus?
Oh, yeah. So, yeah, I guess these pictures are this picture of the surface code. I guess it's the idea of periodic boundary conditions. So you just you put in another check here that checks the last bit and the first bit. And that's also an example of one of these redundant matrices. So there will be a meta check for such a matrix. And then yeah, this picture will end up being wrapped around. So this edge will wrap around to this edge, and the top will wrap around to the bottom, and you get a torus. Yeah.
Okay, I see. I see. So here, the only parameter is basically size of the torus, the size of this grid. Yes.
Yeah.
Okay, fine. So if there are no further, are there any further remarks or questions? Well,
maybe I would like to ask first also a remark concerning what an efficient code is, or kind of the goodness of the code. And in my opinion, one of the advantages, and also why Google is looking for this particular type of surface code, is the corresponding decoding algorithm and the complexity. There are clearly better codes which are of different types. If you just look at the rate and the distance, and already in the paper by Calderbank and Short, they showed that you get asymptotically good codes, which means that the amount of information divided by the length or the number of qubits you are using for the code, that is kind of staying positive if the length increases, and also the fraction of errors you can correct. So that's the kind of the standard way of calling that what a good code is. But on top of that, you are asking the question, what does it cost me to find the most likely error, or at least a subset of the errors? And this decoding performance, that is something that comes with all these kind of topology-inspired codes. Yeah. In the end, it's not the topology, in particular, if you have a high-dimensional kind of a space of which you use the topology, you can never map that down to your main two-dimensional or even just one-dimensional arrangement of your qubits. But nonetheless, the question is the kind of how good can you, or how fast can you perform the error correction steps? And related to that, my question is, what does the point of view from category theory buy you when you think about these decoding algorithms? Kind of, can you explain them or derive them better if you use category theory?
Yeah, those are very interesting questions. And I guess one answer is that I don't really see the category theory as helping the theory that much. It seems like these things are understood, like the hypergraph product construction was understood without using category theory. It was only later on that people realized, oh, hey, this is the tensor product of chain complexes. So I feel like the category theory is more for conceptually explaining, why does this stuff show up? Like, why are these calculations working as well as they do? It's not actually for doing the calculations, it seems.
See, my personal attitude is I'm really a fan of using non-orthodox pictures for things.
Yeah.
But at the same time, I put the bar that using this different machinery to explain things should provide me at least a better understanding, if not a means of generalization.
Yeah.
And so far, kind of my very distant view on all this, I'm really at the stage kind of not using that, since I grew up with error correction. So I don't see at that point, without really diving into category theory, the advantage. And I would like, or I challenge people like you to convince me what is the benefit for me to diving into that.
Well, good question.
I know that I'm provoking, and it's really kind of nothing personal.
Yeah, no, these are good questions as well, which I also think about. Why am I doing this? Why am I torturing myself like this? And it's really until you actually work with this stuff, you don't. It's not convincing. From the outside, it just looks like complicated stuff. And I agree, I was very skeptical about this stuff as well, especially the string diagram notation. Like, until you try using it, it's actually hard to know. Yeah. So
yeah, I understand.
I appreciate your skepticism. I do. Yeah.
Kind of Bob Kuke, he kind of convinced me that rewriting rules for circuit diagrams could benefit to go to the pictorial kind of this ZX calculus, or that diagrammatic way. At least they very concretely demonstrated that they could optimize even kind of stabilize a circuit. So there I see the result really kind of is in favor of it. But what's also a general problem of kind of all these approaches is, to some extent, most examples are somewhat toy examples. And so it's in their nature that it's hard to demonstrate the advantage to the outside world.
Thanks. So I think the time is up. Let us now thank the speaker again. So at least we have a chance to learn something about category theory, or how to possibly you can make a connection to codes and quantum codes. And now let me advertise the talk which will be given next week by Alex de Oliveira, originally from Brazil, and now he's in Krakow. And he will tell us a talk about fluctuation dissipation relations for thermodynamic distillation process. So maybe we will distillate something. We'll be the witness of distillations. Yes, Alex? So thanks again. You are welcome. See you next week. And if you wish to deliver a talk this semester, please let me know soon, because the free slots are sold out, are going to be sold out soon. Marcus, we have your talk scheduled. So you are going to be talking soon, yes? Simon, thanks again. Thanks again for your talk, and see you again. Bye-bye. Thank you.
Bye.
Thank you all guests, especially from South Africa, from far away, also from Madrid. And please come and join us soon. Thank you, Vinayak, Moises, for your remote presence. We hope to see you soon in Krakow. The weather is better, snow melts down. We are expecting spring. Yes, Simon, is it true in Krakow?
Yes.
Good, good. Bye-bye.
Bye-bye.
See you next time. Thanks again.
Bye.